recorded webinar, and we would hope that upon completion of your evaluation, we will be sending out the link to your registered emails. So just want to do a quick sound check. Hi, Greg. Good evening to you.
Hello. Good to see you.
Right. So I see all our participants, and Patty from Erudite will also be admitting those who are coming in. And as she mentioned, we are live on Facebook. So if you are in the network, you may share the live feed from our Facebook page. Patty will be sending out the link to your chat, to the chat box. And all right, so let's go ahead and get started. So welcome again, and just a little bit of who we are. So we are Erudite Reliability Services, OPC. We are a duly registered corporation here in the Philippines, and we're very glad that Greg from the USA are taking time to share his knowledge and expertise about the topic today. Apart from being a training and consulting company based in the Philippines, we also provide certification training preparations for the following: Vibration Institute, Infraspection, ASQ Certified Reliability Engineer, WPIAM for Certified Asset Management Assessor, as well as Certified Maintenance Reliability Professional from SMRP. I know that the pandemic hasn't been very good to everyone, but we are still very lucky and very grateful that our clients have trusted us for their training needs for the past almost 2 years. So we've ventured into a virtual instructor-led training. So we have a live facilitator like Greg, who's facilitating the training for us on this webinar. And here is just a sample list of our clients. And we hope that we could have you in our upcoming trainings and avail of our consulting services through our partnered consultants like Greg here. So why don't I have Patty help me out and introduce our facilitator for today.
All right, so thank you. Our speaker is a voting member of the ASME API Joint Committee on Fitness for Service, API 579, ASME FFS1. Yes, and he performs computational mechanics and fitness for service assessments for a variety of industries using API 579, as well as supporting litigation and failure analysis. He develops specialized software and methodologies for structural analysis and live assessment. Previously, Dr. Brown was the chief engineer for Team Quest Integrity. He joined Dr. Ted Anderson in 2001 at Structural Reliability Technology, which later became part of the Quest Integrity Group. Dr. Anderson, Dr. Brown, and the engineers at Structural Reliability Technology performed much of the work that was incorporated into API 579. Prior to SRT, he developed algorithms to update industrial finite element models using experimental measurements and performed the flutter analysis of F-16 and F-18 fighter aircraft. So without further ado, everyone, please welcome Dr. Gregory Brown, the principal owner of Blue Ring Engineering LLC.
Thank you for that. Let me share my screen here. Thank you for that introduction. I really appreciate everybody joining. We're going to cover things pretty quick, just kind of give you an introduction to what the full course would actually have in it. Obviously, we can't teach you everything about fitness for service in 1 hour. I'll try to leave a little time at the end for questions if anything comes up. So you can see my email's there if anybody would like to reach out, or please reach out through Erudite Reliability. So thanks, Patricia, for the background. As I said, I'm a voting member of the 579 committee. I still do a lot of work developing that standard. My background is actually in aerospace engineering, as opposed to pressure vessels or pipelines or piping, but it was really in the area we call computational mechanics. What that is computer simulation of structures. So finite element analysis computational fluid dynamics, etc. Until 2021, I was the chief engineer for Team Industrial Services. They're a provider of industrial services throughout the world, very busy, especially in the downstream industries such as refining, petrochemical, etc. They provided inspection services, mechanical services such as welding, bolting, etc. I was in the advanced engineering group, which used a lot of those inspection results and really did a lot of assessment of various equipment to determine if it could stay in service. What I do now is I still do fitness for service, still very active in the committee. If anybody's interested in the 579 committee, we are actually meeting on Monday and Tuesday next week, Tuesday and Wednesday in the Philippines. One question that does come up, so I like to bring it up. My company is called Blue Ring Engineering. It's my own consulting firm now. Yes, I did name my company after an octopus. I had to come up with a name for a company. My wife was looking at scuba diving photographs, actually photographs from the Philippines at the time. And there was a picture of an octopus, so that's what I named my company. So what you're looking at in the picture on the screen, everybody can see my screen. Patricia, is that showing up? Okay, very good.
Yes, Greg, we can see it.
That is actually from a litigation, a court case regarding the failure of a Learjet that crashed and killed all its passengers. What you're looking at is a computer model of what's called the cockpit outflow adapter. This was what regulates pressure in the cockpit. So that kind of gives you an idea of some of the advanced modeling I do. Anytime you see a colored picture with little boxes that you see, that is what we call finite element analysis. It is just a fancy tool to allow us to compute stresses, strains, etc. So what is fitness for service? Why do we like to do it? Well, basically, whenever equipment has damage or is operated beyond the design parameters, it is no longer covered by the code of construction. For instance, a pressure vessel might be built to the boiler pressure vessel code Division 1 or Division 2. If you have, for example, metal loss that is beyond the design, you are no longer covered under the design code, and we do fitness for service. So the objective is to determine if that equipment is safe to operate. And when I say safe to operate, it is usually until we can inspect the equipment again. For instance, the next turnaround at a refinery would be when we would inspect the equipment again, or the next shutdown. So this could be because it has damage, metal loss, cracking, etc. Maybe it was operated too hot, etc. This is what we assess it with. The decision of a fitness for service is, can we continue to use the equipment? How long can we use the equipment? Or do we need to repair or replace that equipment? There's a lot of different types of damage we encounter, and most of these are going to be covered in fitness for service. Now, here I am talking about the fitness for service standard API 579/ASME FS1. It's a very long name. Most people call it API 579. The same methodology and many of the same methods exist in other fitness for service codes. For example, there is a British code that is BS 7910. In the pipeline world, if there's pipeline operators on the call, you'll run into B31G. Many of these methods are very similar. A lot of the committee members actually serve on multiple committees, so we share a lot of information together. So when we talk about damage, what type of damage do we have? Well, we can have what are called pre-service deficiencies. What are these? Fabrication defects. Maybe our welding was not done properly and we ended up with cracks in the weld, or porosity, or bad material properties. These are things that happen in fabrication. Hopefully we can find these with inspection before we put the equipment in service. You can get damage due to mechanical operation. A good example is fatigue damage. We have cycles on equipment. So imagine pressure oscillating. This can eventually initiate a crack. That crack could then grow and cause failure of that equipment. You could have high temperature damage. This is when you operate equipment At too high of a temperature, you can get creep damage, as it's called. Creep damage is where you're actually creating voids in the structure. This eventually leads to cracking and eventual failure. It requires time, temperature, and stress for that to occur. You can have environmental damage. Most common environmental damage we encounter is corrosion, of course, where we have metal loss that reduces our wall. Can we still hold our pressure? Other types of damage, you can have stress corrosion cracking is environmental. Hydrogen damage, you can get blisters or cracking. You can get high temperature hydrogen attack. Microbial corrosion, that's when you actually have organisms that are causing corrosion. I always like to imagine is little amoebas eating my pipe. That's not really what happens, but it does actually cause metal loss. So 579 allows us to assess most of these damage types and then determine if they can stay in operation. Here's some just pictures of damage from various cases. In the upper left, you're looking at a computer model of what's called a hook crack in an ERW pipe. Electron resistance welded pipes very often get crackings at that weld. You get what are called J cracks or hook cracks. In service with pressure cycles, these can grow and can cause failure. So what you're looking at in the picture is you're looking at a computer model to determine the stresses at the tip of that crack. So then we can determine, will that crack remain stable? How fast will that crack grow? And then, does that give us enough time to operate? When do we need to repair? When do we need to replace that equipment? Picture in the lower left, this is an example of hydrogen damage. If you ever have a carbon or low alloy steel and you have the presence of hydrogen, you can get hydrogen damage. Blistering is one type of hydrogen damage. You can also have what's called hydrogen-induced cracking, or also you can have stress-oriented hydrogen cracking. A lot of different types of damage due to that presence of hydrogen. 579 is going to give you guidelines on how to assess those. In the middle, you see metal loss. This is external metal loss. This is actually not corrosion. This is actually metal loss due to a repair where they ground out cracks. We want to know if we still have enough wall thickness to safely hold that pressure. So this is a computer model to determine if that equipment is still safe to operate. In this quick webinar, you're going to see a lot of computer models because that's a lot of what I do. So they're good examples to show. Also, people like colored pictures, so I can show those a lot. Here's another example of fatigue damage. This is a wind tower. There's a lot of interest in renewable energy now. A wind tower is basically a beam that bends in the wind. If you have a crack, that crack can grow and eventually cause catastrophic failure that you see here where you collapse the tower. If you looked at failure surfaces on that wind tower, you might see fatigue striations, which you see in a scanning electron microscope. Very obvious that this is growing by fatigue. So again, this course will tell you, how can I assess fatigue damage? I have a crack. I want to know how fast it grows. When do I need to inspect again? Now, in 579, as well as other fitness for service standards, even inspection codes, you're going to see very often what's called a level 1, 2, and 3 assessment. The idea is that this would be the escalation you do when you encounter damage. Now, a level 1 assessment is designed to be very, very conservative. It's designed to be something quick. So it's very often you're looking up on a graph or a figure if that equipment is safe to operate. In 579, this was actually designed to be used by a trained inspector. They said in the field that really doesn't happen. Usually it's at their desk, of course, but it allows them to do some quick calculations to determine if that equipment is safe to operate. In the course, we will actually cover the entire level 1 assessment. We will go through it step by step and allow you to do classroom examples on some of the damage types, particularly on cracking and on metal loss, which are really the most important parts of the standard. Level 2, it still follows a very precise roadmap. You follow step-by-step directions. except the calculations get a little more complicated. So this needs to be done by an engineer. Now, what defines an engineer? That is up to the owner operator if they have sufficient experience. Is it a college degree? Is it an engineering license? Is it so many years experience? Is it some lack of fashion sense or social awkwardness being an engineer? So the level 2 takes away some of the conservatism of level 1, but the math gets more difficult. So very often you're going to want to use commercial software or a well-programmed Excel spreadsheet, for example, to do those calculations. In the course, I don't make you do level 2 by hand. That would take a long time, but we will go through what the level 2 involves. And then finally, you have level 3. Level 3 is everything else. This is where you go to the realm of experts, consulting firms. This may use tools such as finite element computer analysis. What you're really doing is you're changing some of the assumptions in the level 1 and level 2 analysis. So typically what you would do would be do the level 1 quick screening. If you pass, you're comfortable operating that equipment. If you don't pass, maybe you proceed to the level 2. Now, if you don't pass the level 2, do you need to do the level 3? Maybe. It really depends. Why are you doing the level 3? If you have a pressure vessel and you've lost 80% of your wall, doing a level 3 is not going to help you. You just don't have enough metal to carry your internal pressure. It might give you a more accurate answer that you can't use that equipment, but it's not going to actually help that equipment stay in service. So level 3 is the realm of specialists. Larger companies, this would be where corporate engineering gets involved, outside consulting firms, etc. So we'll talk about some level 3 examples, but I cannot train you to do level 3 analysis because everyone is unique and different. Oh, by the way, if there's any questions, as he mentioned, we'll have some time at the end. Please just type them in the chat window or hold them to the end, and then we can actually talk about those. There's a lot of different areas that get involved in fitness for service. You may be familiar with stress analysis. This is basically computing how much stress is acting in my wall. Maybe this is a hand calculation. Maybe it's a computer model. Maybe it's a piping program like Caesar, etc. Metallurgy and materials are a big part of fitness for service. One of the best ways to avoid damage is to actually use a less susceptible material, which is almost always more expensive, of course. So understanding what the alloy is can really help determine what damage you need to be concerned about. NDE, or inspection. Now, fitness for service is not a replacement for inspection. Instead, it is designed to work together with inspection. You get an inspection done, you get that report, then you do a fitness for service to determine if that equipment is acceptable. Now, what we'll do in the course, we'll talk about how you can actually use fitness for service calculations to actually determine when you need to inspect equipment again. Do you need to inspect in 2 years or 5 years or 10 years, etc. Corrosion, a big part of damage is understanding corrosion. Why does it occur? Can you change operating conditions to avoid that corrosion? And then, of course, plant operations. How does that equipment fit into your operations? A fitness for service calculation may tell you you need to operate at lower pressure, but of course, if that doesn't work, then that answer doesn't help you too much. Fracture mechanics, it is a fancy word to say, how does a structure, a pressure vessel, a pipe, a storage tank behave with a crack in it? That's really where I was involved most in 579, as well as my former boss and now a colleague I work with, Dr. Ted Anderson. In the course, we will give you an introduction to fracture mechanics because the crack assessment in 579 is really the most powerful part of the standard. I'm sorry? I may have just been a mute button. Okay. So if you're more interested in fracture mechanics, there's a longer course that you might be able to take. And finally, probability and statistics, that comes in as you look at risk on equipment and how to operate it. We'll talk a little about inspection in the course, about different inspection types, what is useful to detect different types of damage. Now, I'm not an inspector, so I'm not going to give you a detailed course on inspection, but we'll talk about different methods and when they tend to be most useful for different types of damage. Typically, for most types of damage, what we find most useful is ultrasonic inspection, because this allows us to look below the surface. Phased array ultrasonics, which we'll talk about in the course, is really probably one of the best tools I've seen to do fitness for service assessment. And you can see some pictures on the side. The upper one is a visual inspection using dye to find cracks. The middle picture is some ultrasonic inspection. And then the bottom picture is X-rays of a weld looking at cracking and weld porosity. Now, one thing about fitness for service you can also think about is it can also be used in a different way. Now, typically we have damage. We want to know if we can operate the equipment. But what we can also do is, can we use fitness for service to justify operating our equipment differently? A good example would be if I have a piece of equipment that is making some product, maybe it is a reformer, for instance, fancy type of equipment for chemical reactions. If I can operate that equipment at a higher temperature, I can actually be more efficient and make more product. Now, depending on my market, maybe that allows me to make more money. But fitness for service guidelines can be used to determine, can I still do that safely and then maximize the value of that piece of equipment. And then the picture you see up top is probably obvious. Looks like a salesperson made it. Obviously, the cost and time to do an assessment is much, much less than ever an unplanned outage or replacement of a piece of equipment. What goes wrong without fitness for service? This is really what we want. Oops, stop scrolling. So this is what we really want to avoid. What you're looking at here is the failure of a large pressure vessel. The thickness of this pressure vessel, I think, was on the order of 6 to 8 inches, 200 millimeters, something like that. And what you're seeing is this failure occurred because a crack near the weld, what's called the heat affected zone, started, and then upon pressurization, it immediately propagated in a brittle fashion, went through the entire pressure boundary, the entire wall of the vessel, and actually caused catastrophic failure. What you'll find on fitness for service is most failures actually occur at weld locations. Not all of them. Certain types of damage don't occur at welds, but cracking failures, for example, almost always occur at a weld location. This failure actually, I believe, killed 4 people and caused multiple injuries. So obviously, this is what we want to avoid with fitness for service. We can actually use the material in 579 or other standards, as I'll show you in the course, to determine what size crack is stable and doesn't pose a risk for catastrophic failure. Now, in the course, we'll go through the entirety of the standard. Parts 1 and 2, just introductory material, not a whole lot there. Very much what we're doing now. I actually use some of that material in this webinar. What is fitness for service? Why do we do it? What are the assessment levels? A big part of the standard for a lot of people are parts 4 and 5. This is metal loss, corrosion, erosion, could even be mechanical damage such as grinding. That is really one of the most important parts of the standard. So we will go through that in detail and actually go through examples step by step, as well as allow you to do classroom examples for metal loss. Other types of damage you'll see pitting, corrosion, for example. This question came up, but I'll read that a little bit later. Thank you. Pitting corrosion obviously occurs due to environmental effects. How do you assess that? Talked about hydrogen damage, hydrogen blisters, hydrogen-induced cracking, stress-oriented hydrogen cracking. Part 8 is about misalignments. A pressure vessel should be round, gives us a nice even hoop stress field. If it's not, we start getting higher stress, bending stress. this can actually lead to a failure, very often due to fatigue. The guidelines in Part 8 will tell you how to assess those types of out of roundness, weld peaking type situations. Part 9 really to me is one of the most important parts of the standard because it's really the most powerful, assessing crack-like flaws. This could be weld defects, lack of fusion. This could be fatigue cracks. This could be stress-oriented hydrogen cracking. This could be stress corrosion cracking. A lot of different types of cracks can occur. Part 9 allows you to assess those. And with a level 3 assessment, you can actually start doing crack growth calculations to do fatigue life, for example. So we'll go through that in detail. In the course, I'll actually give you an introduction to fracture mechanics. A lot of the parts in the standard are very similar to other fitness for service codes, but Part 9 is really one of the most unique and powerful parts of API 579. Part 10 is about high temperature damage. What happens when we operate our metallic alloys, our steels, etc. at high temperature. We do what's called creep damage. This eventually leads to cracking and leads to failure. So assess that. Part 11, hopefully nobody will ever use. What happens when you have a fire at your facility or in your pipeline or in a storage tank? Can I still use that equipment? What about other equipment that was exposed to the fire? Is that equipment still safe to operate? Part 12, dents and gouges. This is a big concern in the pipeline world, particularly for third-party damage. There might be a buried pipeline. Somebody's installing electrical wires or cable television. They dig, they hit a pipeline, cause a dent. If you don't know about that dent, with your pressure cycles, it will sit and do this. It will re-round. It will kind of move in and out, eventually causing a fatigue crack. That crack can then grow and cause failure of that pipeline. Laminations, these are just cracks that are oriented such there's not much stress opening them. This is really just, they're really typically benign. And then finally, Part 14 is talking about fatigue damage. When can I initiate a crack? So in the course, we'll go through all these damage types and go through step-by-step how to assess them. But the core of the standard really is parts 4 and 5 on metal loss and part 9 on cracking. Many of the other parts of the standard and other standards actually will reference back to those parts. So we have 30 minutes or so left, but I want a lot of time for questions. So let's show you some examples of some fitness for service that we did. These are really quick examples. I use one of these in the course. I note that these were actual clients. These were actual assessments that were done. So I did have to remove a lot of proprietary information. I had to sanitize them to be shown publicly. So what we had in this case, we had what's called a CO2 absorber tower. It is a tall, narrow pressure vessel, and it had regions of metal loss in the shell. There was 4 regions of metal loss. An inspection was done to determine how much wall thickness was there. As it turns out, this metal loss was below the designed minimum thickness. Now, this kind of goes a little bit towards the question, which we can answer later. If on your equipment, if you have more thickness than your design minimum, you are covered under your code of construction and you do not need to do fitness for service. Fitness for service only occurs when my thickness drops below my design thickness, my T-min as it's called, and that's what causes a fitness for service. So in this case, there was 4 areas that had some thickness readings that were less than the required thickness according to the design code. What we did was we actually did a level 2 fitness for service assessment on each of these. This involves doing step-by-step calculations where you're computing kind of a average thickness and comparing that to how much thickness you need. Again, in the course, we'll go through that step-by-step. Turns out that one of those 4 areas actually passed the level 2 assessment. So that area was no longer a concern. For the other 3 areas, we actually did a level 3 assessment using computer modeling, what is called finite element analysis. In this case, 2 of those areas passed level 3 assessment. They were now acceptable, but the last area did not. There was just too much wall loss, and it was actually located near nozzles. So we actually did a repair on that vessel, but we actually validated the proposed repair using finite element analysis. So let me show you what this looks like. On the left side, you can see what the vessel looks like. There was 9 shell courses. There was a support skirt on the bottom. And the areas we are concerned with, you can see highlighted by this green box. There was 4 grids, as they called it. It's called the grid because they took measurements on a grid on the vessel. A couple of these areas were around a patch plate where repair was done previously. A region of the vessel was cut out, and then a new piece of metal was put in. So some of that damage may have been due to overheating or material damage that led to corrosion around that patch plate. So you can see these grids 1, 2, and 3 kind of near that patch plate. Thickness measurements were taken for all the grids. We used those to do the fitness for service assessment. Again, fitness for service is not a replacement for inspection, but is working together with inspection, although it can help you determine what type of inspection do I need to do, how much resolution do I need, when do I need to inspect again. Finally, what you see is on grid 4, this was around these nozzles in the second shell course. The grid was a 1-inch inspection grid on all locations. Now, one thing about a tall vessel like this, it actually, you're concerned about loads other than just pressure. Yes, you have pressure on the vessel, but on a tall vessel that's located outside, you actually have wind loads that were actually acting on this vessel. You had to actually take into account the effect of those wind loads when you did this assessment. Now, if you ever have wind loads, we'll talk about a little bit this about in the course. I would recommend to, if you need to estimate those, there's some civil engineering codes that allow you to determine what loads you need to include on the structure. So what you're looking at is the 4 locations. These are actual photographs. The grid you see was a manual grid used to do ultrasonic inspection. So the inspector drew the grid out and then was doing straight or compressive ultrasonics at each location to get a wall thickness measurement. It works really well to get thickness measurements, ultrasonics, but you need to have access to the surface, you need to have a clean surface, etc. It doesn't work through things like insulation, etc. You need to look at other methods for that. So grid 1, you can see, is not too bad. Some kind of bands of corrosion near this circumferential weld. We also have some patches of corrosion located at the edges of this patch plate, as you can see. You can see the grid over on the side where they took some thickness measurements. Note on this vessel, you can see in the pictures external corrosion. There was also internal corrosion we had to account for as well. In the lower left, you can see the patches of corrosion around the patch plate. And then finally, over here on the lower right, what you're seeing is patches of corrosion in the second shell course near these nozzles. So the grid 1, as you see here, this passed a level 2 assessment. This is good to stay in service. A level 3 assessment was done on the other areas. You can kind of see some pictures of this here. Again, anytime you see these colored lines, it means finite element analysis was done. There's nothing magical about this. It is just a very fancy calculator used to compute stresses and strains, etc. So what you're looking at on the upper pictures here, you can see the corrosion around that patch plate. In this case, what we did was we actually matched or used the inspection grid and actually put that into a computer model, used all the inspection points. And what you're looking at here is stresses under those operating conditions, pressure and wind around that location. And you can see some higher stresses occurring where there was this corrosion. So the corrosion is actually causing a region of high stresses. As it turns out, these locations actually passed the level 3 assessment rules. We'll talk about those assessment rules in the course. But the other corrosion that you can see on the bottom was located near these nozzle locations. Anytime you have corrosion at a nozzle or other structural discontinuity, the level 1 and level 2 assessment will not apply. It automatically causes you to do a level 3 assessment. In this case, that's what we did. You can see some higher stresses occurring at the nozzles. As it turns out, this did not pass the level 3 assessment. So they went to a repair situation. To stay in operation until they could do a longer shutdown, they actually did an external repair where they actually welded patch plates on the outside of the vessel. So what you can see in this picture is the diagram of the repair, where we have a 1/2 inch or 0.625 inch plate that was welded around those nozzles. It had to be done in multiple pieces so it could fit around the nozzles. The purple lines you see are the welds between plates, and then there was a fillet weld around the edge. This is not a permanent repair. This was a temporary repair till they can actually do a more permanent repair. How did we validate the repair? We actually modified our corrosion model, our computer model, with the proposed repair, which you can see the various patch plates included. Turns out that repair was acceptable. So this was completed. The equipment successfully stayed in operation until a longer shutdown when they did a larger repair. I don't particularly like patch plate repairs. I would typically prefer a full encirclement repair. So you're making sure you can handle that hoop stress, but in this case, it was acceptable. And if you have any questions on this, please type them in the windows and we'll go through those in a little while. Another example where we applied the fitness for service was a tank settlement. Now, this tank actually had some other issues such as metal loss as well, but we'll talk about settlement here. The guidelines for tank settlement are very often in API 653. This has limits for allowable tank settlement. So basically what's happening is the edge of the tank is actually dropping down. So the soil underneath it is settling. This is causing the tank to deform. What does this do? This causes higher stresses in the tank, and it may not be safe to leave in service. So since it did not pass the 653 requirements, we went to API 579 and did fitness for service. This was a level 3 fitness for service. We used various finite element models. In this case, I'll talk about a what's called an axisymmetric model of the floor, shell, and roof. And in this case, the level 3 requirements were actually satisfied. That tank settlement was acceptable, so the tank could stay in service. Otherwise, what you would have to do would be to jack or lift the tank and repair the foundation and possibly repair the floor of the tank as well. So let's show you what this looks like. Oh, sorry, let me go ahead a little bit. This was actually the measurements around the edge of the tank. There were some other measurements as well. And what you can see is on the horizontal axis, this was the location around the tank, various measurement locations. And then the blue line is the actual measurements about how far the tank was away from the nominal or optimum configuration. As it turns out, the tank was actually, the way this is plotted, a positive measurement actually is a downward deflection. And then you can actually use those measurements in API 653. The tank code, it did not meet those requirements, so we did a final analysis with 653. Or sorry, with 579. Now, when we do a level 3 analysis, there's various rules we have to meet. We have to evaluate what's called plastic collapse or instability. What this is, the loads on the structure are so high that it overcomes the yield and tensile of the material. The entire material comes apart and causes failure. So there's a set of rules for plastic collapse. This is an instability in the structure. So the way the rules work would be, since this is a physical case where the structure goes unstable, if you build a appropriate computer model, a physical instability should cause a instability in your computer model. So we can use a computer model to determine if a structure is stable. Then we put on additional factors of safety. You also have to evaluate what's called local failure. This is making sure you don't get too much what's called plastic strain, permanent deformation at locations on the tank. And that just has to be less than a limit. Sorry, the slide had an equation. Probably shouldn't put equations in this, but you evaluate the plastic strain against a limit. If it's under that limit, that is acceptable, you pass that. In addition, you might have to do some other checks for a level 3 analysis. If you have compressive loads pushing on the structure, you have to make sure the structure wouldn't buckle and fail that way. If you have cyclic loads, so the pressure is oscillating, for example, you would need to do a fatigue evaluation. Oscillating loads can also cause what's called ratcheting, where on each cycle you start getting more and more strain, and this actually causes a low cycle fatigue failure, where the structure could actually fail in a relatively low number of cycles. So here's an example of a computer model. Maybe a little tough to see, especially if you're on Facebook. The blue is the floor of the tank. The light blue is the roof of the tank. That's really only there to put the weight loads due to the roof. We put product in the tank to put all the loads on the floor, the hydrostatic stress on the outside. The tank shell is in green, and then you have this floor to shell weld called the chime weld in the model as well. This location is usually the most critical location for storage tanks. What an axisymmetric finite element model is, you're actually capturing the full three-dimensional stress state, but you're just modeling a single slice of the structure, and you're assuming it doesn't vary around. It's just a more computationally efficient way to do things. But since we're worried about settlement, how do we actually model tank settlement? Well, we take that model and we put it on the soil, on the foundation. We give the soil the shape that was measured, and then we put the load on the tank, allow the tank to settle into the floor. What this causes is the bending you see in the tank floor and the shell. We can use that to determine if it's acceptable. So here's an example of the plastic collapse analysis that was done. As it turns out, the structure remained stable under the loads, even with the factors of safety that are required. What you see is the tank shell here kind of bending outward, and you see high stresses. In this picture, this is what's called von Mises stress or equivalent stress, occurring right at that floor to shell weld. Usually this is the key location. You get significant bending stresses at this location, especially for tank settlement. This is usually the case that will actually govern the assessment. Local failure, you're looking at plastic strain, how much non-recoverable deformation you have. And in this case, this is the plastic strain plotted. And we are actually getting, again, plasticity occurring at that location, but it wasn't so significant that it did not meet API 579 limits. So the result of that was that it met all the requirements. So that tank could stay in service. They did not have to repair the floor of that tank. This same type of analysis is very often used for other tank assessments. For example, if you have a repair on a storage tank, you're usually required to hydrotest that tank. Now, what is a hydrotest? You fill the tank, you hold it, you make sure it remains stable. This can be very expensive to conduct. So what we can do is we can use the rules in 579 to actually give you an exemption for a hydrotest. So what that means would be we use some analysis, we look at the inspection that was done of the repair, of the welds, etc. We make sure that any flaws that exist in those welds would still be stable and acceptable. If you meet those requirements, then you are actually exempt from the hydrostatic testing, which can be very, very significant cost savings. We'll talk about hydrotest exemptions in the course as well. So that was kind of the quick introduction. to fitness for service. Again, why do we do it? We no longer meet requirements of the construction code. In the course, we'll go through all the various damage types and how you assess them. We'll do step-by-step on level 1, including classroom examples. We'll talk about the level 2 analysis and go through that as well. And then we'll discuss level 3 type analysis. So I really encourage you to join. The course is appropriate for engineers and inspectors. There is some math involved. We do example problems, but it is nothing that is too painful. Most people who take the course are engineers. We do get some inspectors. So some familiarity with concepts such as stress, strain, inspection is very helpful. But we also still get even sales and marketing people and managers that take the course every now and then. I've taught the course for, I think, 10 years or more, and to a lot of different industries and types of students. What you'll find is in 579, certain parts are going to be more important to you based on your equipment that you're concerned with. Are you a pipeline operator? Are you in refining? Are you from aerospace, etc. So with that, I wanted to leave 10-15 minutes at the end to see if there was any questions or discussions. But other than that, feel free to reach out, and I hope to see you.
Thank you, Greg. We do have a few questions on from the chat. If I may share the
Yeah,
screen.
I have it over here.
Yep. So
okay, so a couple things. So I think Muhammad was asking about, let me stop. Oh, you have it. Okay.
Yeah.
He was asking about the acceptance criteria in part 4 of 579. What he's asking about is there's a requirement that no matter how the calculations turn out, that the minimum measured thickness that you have is less than this limiting value. What the limiting value turns out to be is it's actually, I think, 0.2 of your original thickness, 0.5 of your minimum thickness, or 1/10 of an inch. And then for piping in the current version, that 1/10 of an inch requirement has actually been relaxed to 0.05 because there's thin wall piping. So really, if you don't meet that requirement, your only option is really to do a level 3 analysis to have some reason why you could operate that equipment when you're below that limiting thickness. One concern with metal loss is the rules are all about what's called tensile overload or plastic collapse. When you just don't have enough wall, the entire structure comes apart. There's not any checks in that section for things such as pinhole leaks, etc. So there's always going to be a minimum amount of thickness that is required. So if you don't meet it, you could consider a level 3 analysis. But again, it depends which limiting thickness you don't meet. If you've really lost 80% of your wall, it may be time to think about replacement or repair of that equipment anyway. Does that answer your question? You can probably just maybe use thumbs up or type it in the window if you want. So is there a way around it? Maybe it really depends on your equipment and your exact situation. Okay. I think the next question, could you apply fitness for service for chilled water lines? Absolutely. You know, anytime you have a refrigerator or chilled product, you start thinking about thermal events as well. But in addition, we'll talk about this in the course, for our carbon and low alloy steels, as we get colder, what happens is we lose ductility, which means we lose something called fracture toughness. Now, fracture toughness is how resistant a material is to cracking in the structure. So what that means is for our carbon and low alloy steels, as we operate colder, we have less resistance to cracking. That makes small cracks that might have been acceptable at ambient conditions at 20 Celsius to not be acceptable at lower temperature. So yes, you can apply fitness for service to those equipment. Now, from your question, I don't know what type of fitness for service are we doing? Are we looking at metal loss? Are we looking at cracking? Are we looking at fatigue, etc.? But absolutely, you can actually apply fitness for service in those conditions. Now, part of the question that comes up is, what situation are you in? A good example, I was just recently looking at equipment that was chilled water, but it was designed, the chilled water was actually used to cycle a piece of equipment where they had to bring it down from elevated temperature as part of their chemical processing. It was actually a pharmaceutical industry. They had to use chilled water to cool the vessel down so they could reload it. Anytime you take hot equipment and impact it with cold liquid, what happens? You get significant thermal stress. This was causing fatigue cracking, which then propagated and was causing failure of those lines. So in that case, we really did apply the same methodology in 579 to determine what's happening with that chilled line. And we used that to create new operational guidelines regarding how they cooled that vessel down. As it turned out, what you could do, I say vessel because it was actually cooling coils on a vessel. Most of the damage was occurring very early in the cooling process. So what they did was they actually started cooling the vessel slowly at first, brought it down to a little bit lower temperature, and then they used the full cold chilled water to do that. So absolutely, yes, you can apply that. So does that clarify both your questions, or is there other questions? I don't see any in the chat window, but people are welcome to unmute.
There may be some, because I saw Mohammed also just came in. Would there be any clarification so far from those who posted their questions? You can also raise your hand and open your mic if you have any clarifications. All right.
Okay, I think it's enough.
Okay.
Thank you.
Thank you, Mohammed.
Was there any other questions? I saw, I guess the clapping hand.
Yes, a clapping hand. Okay.
Yeah, which I guess it means they're happy. So,
Right.
so I think that's it. I didn't want to take too much people's time on the introduction.
Right.
Was there
Me-
any? Oh, go ahead,
Yeah.
please.
Yes, so Greg, I would also like to take this time to request everyone to, oh, okay, Jeff, you raise your hand, please raise your question.
Sir, can I ask something about remaining life?
Say that
About
again, sorry.
remaining life?
Oh,
Yeah.
remaining life, yes.
Yeah. In pressure vessel, have a formula like how to how to find remaining life is thickness actual minus thickness required and per corrosion rate, right? And so if in case we have a thickness actual is same with thickness limit.
Zeph, it's breaking up on my end. Would you be able to type in your question via chat?
Yeah. Okay.
Yeah, that might be easier. I was having a little trouble.
So I mean, why we don't make thickness required same with thickness limit? Because limit is the next the last level of thickness.
What you're saying is, how do we do remaining life when you have the?
Yeah, how we do remaining life if in case thickness actual is same with thickness limit. Thickness limit is 2.5 millimeter.
The thickness actual is the same as the thickness limit?
Yes.
Then in that case, you're not going to be able to compare. If you're really at that limiting thickness, that 2.5 millimeters, 1/10 of an inch, you're not going to pass the level 2 assessment, or you pass it today, but you're always going to need to, when you do the assessment, include a future corrosion allowance as well. So if you're right at the limit, when you apply any future corrosion allowance, obviously you will not satisfy that level 2 assessment. It is possible that a level 3 assessment would help you, but that can be challenging because you need to justify why you could operate a location with very, very thin wall. So typically when you're getting down to that limiting thickness, you have some significant concerns regarding can I leave that in operation? Now, if you're above that limiting thickness, you can definitely keep remaining life, but to do that, you need a corrosion rate, of course, which can be challenging to estimate. But once you have that number, you can estimate how long it takes your thickness to go down to that value. But if you're really down to that thin of wall, you can consider doing some level 3 analysis, but you're so thin at that location that it might be time to consider looking at repair or replacement. The exception I've seen where people have used more analysis to justify would be repurposed equipment that was actually in operation at a higher pressure in a corrosive environment, but now is used at a much lower pressure and no longer a corrosive environment. So they don't have any concerns with ongoing corrosion. The pressure is lower. Maybe that equipment met a hydro test, for example. There's no reason to expect it to fail because you don't have corrosion. In that case, they left the equipment in service. But does that apply to your situation? That really comes down to how far away you are from the limit and what type of service and your own risk analysis that is done. We didn't talk about risk, but risk is really probability of failure times consequences of failure. 579 can help you with the probability of failure, but it cannot help you with the consequence side of it. That's where you need to go to other codes. There's a question from Mohammed. 80% thickness is a rule of thumb. No, it is actually a rule that is written in 579. Let's see if I can bring this up quickly. So it is in part 4 of 579. So if I can share my screen, just for example, we'll do this real quick. May I steal the screen? Is that okay? Okay. So to answer your question, for example, this is, if people can see that, I know this is probably a little challenging to see. This is from part 4 of 579. These are all the rules. We'll talk about these in the course. But at the bottom, you see that the minimum measured thickness has to be less than this limiting value, what you're talking about. So that you have to have at least half the design minimum or this limiting value, which you see is 0.2 of nominal. So 0.2 of nominal means I have 20% of my wall left, which means I've lost 80% of my wall. That answer your question? Okay, probably good. So we have a minute left. Anything else?
Sure. Can I ask again?
Yes, go ahead.
Yes. Okay. So, do you have any recommended software to use fitness for service? Like in one software, have a level 1 or 2 and 3?
Well, there's a couple different things. I'm not in software sales, so there's multiple programs out there, and it really depends what type of damage and what type of equipment you're assessing. When I was at Quest Integrity, we had a program called Signal Fitness for Service, which I liked. Very intuitive step-by-step interface. It covered most of the damage assessments in 579. Another piece of software is made by a company called Equity Engineering, called VC Sage. Again, fully featured, very powerful, has most of what you need. But there is other fitness for service tools out there. For example, if you're looking at metal loss, the company that's called Codeware, I think they did a lot of the design software for Div1, etc. I think they called it Inspect, where they actually had a code to assess metal loss in that. So that works pretty well. That was very easy for them to implement because they already had all the thickness calculations done as part of their design software. There's other software out there. If you're looking at cracks, for example, there's a program called CrackWise. You can also, depending on the damage, do a lot of this in a spreadsheet. For example, something like creep damage, very suitable to write into a spreadsheet. I've actually had clients where my entire job was to write them a spreadsheet so they could look at creep damage. So there's a lot of tools out there. What's the best tool? Well, the best tool is any tool you have, of course, but it also depends on what damage you have. There's always more software coming out there. We're starting to see more software that actually connects to existing software. For example, fitness for service software that is designed to work with finite element software or a piping program, etc. With the exception of a few such as Sage and Signal, most of them are not fully featured, meaning they do every type of damage in every situation, but they focus in on some specific types of damage. I would also note that it depends on your application. Programs like Sage and Signal are very good for when you are looking at a piece of equipment in a refinery, for example, that has corrosion. But if you have millions of measurements from an inline pipeline inspection, that's not going to be the best tool for you. It might be the right tool to look at a very localized location, but it is not the right tool to assess an entire pipeline. So it really depends on your application. Okay.
Okay, thank you so much, sir.
So like every answer in fitness for service, the answer is usually, it kind of depends on your situation. So with that, I think,
Yes.
unless there's other questions, I'll let you close this out, and I hopefully we'll see you, when we do this course.
Right. And would like to take this opportunity to thank everyone for joining us, especially for Dr. Greg Brown, for sharing his knowledge and expertise. Can we give him a big round of a virtual round of applause? Okay. Thank you so much, Greg. And as you see on our screen, he is facilitating our full day course on API 579 on November 16 to 19, and we hope to have you there and to learn more about our topic. And I also would like to invite you to answer our post-evaluation webinar so we could know your experience on this webinar, and in the spirit of continuous improvement, we'd love to hear your suggestions. So with this, I would like to say thank you very much for everyone's time and sharing your insights and asking questions so that we also learn from each other, and most especially to Dr. Brown. And for this, we are Erudite Reliability Services, and we would be happy to have you in our future training program. So on this, thank you so much and enjoy the rest of the day. And for you, Greg, I know you're due for dinner, so enjoy
It's dinner time, yes. Okay, well, thank you, everybody. I appreciate it, and have a good day.
Thank you very much. Bye.